We're going to stay on domain and range today, but I'm going to start working on problems that are a little bit different. Before we start working on those problems, let's review the vocabulary we talked about last class. So again, our objective is to determine the domain and range of a linear function for mathematical problems. We're going to start looking at reasonable domain and range in real-world situations for both continuous and discrete, focusing mainly on continuous today. And we're going to use inequalities to represent this domain and range. So remember, the domain is the set of all input values. That's the set of all x values of a relation or function. And domain, since it's the x's, is read from the left to the right of the graph, like you read a book. The range is the set of all output values, that's the y values of a relation or function. Range, since it's the y values, is read from bottom to top. Now that's least to greatest, but since we're talking about the y values, we'd go from lowest to highest. Now a function or relation has what's called a continuous domain and range if its values are unbroken or connected. So connected together or unbroken. They're not a scatter plot, it's actually like a line or a curve or dots connected together on your paper. If the values are unbroken or disconnected, then the domain and range is called discrete. Now today we're going to be mainly focusing on these continuous graphs because we did really well with discrete last time. But for another quick review, let's just go back over how you write continuous domains and ranges and how you would write discrete domains and ranges. So continuous is that connected data. That's going to be our inequalities. Last time we filled out a little pattern that looked something like this, where you had the left and the right number dealing with the x's, and then you had this pattern with a y in the center for your range, and that was my bottoms and tops numbers. For discrete data, all we did was make a list of the numbers with commas in between. Remember, there is no repeats, so we just need to list the values for both the domain and the range. Now, that's going to be really cool for our graphs with two endpoints. That's what we focused on last time with continuous, graphs with two endpoints. So we were always finding the left and right and the bottom and top. So this was the left and this is the right. This would have been the bottom and this would have been the top. Great. Today, we're going to be talking about domain and range when the graphs only have one endpoint, like you kind of see here. So instead of having two endpoints, do you see how all of these graphs end with an arrow as if they're going off the screen? Okay, that's super important to recognize because that's going to change how we write our domain and range. If your graph only has one endpoint, then you're only going to have one number included in your domain or your range. Okay, the domain is going to be in the form x less than or greater than, less than or equal to or greater than or equal to whatever that number where the graph stops is. And range, the y's, are going to be less than or greater than, or less than or equal to and greater than or equal to some number where all the x and y values are larger or smaller than their maximum or minimum value. Super confusing to talk about, but here's how we do this. So if we're talking about this domain of the first example, remember we wanted to go from left to right. We already noticed that on the right side, there's an arrow. That arrow would go all the way to infinity, as if it's going on and 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 on forever. But on the left, we have this open circle right here. That left is at the value -2. Now, all of the x values where this graph shows up are over here, right, headed off to that positive infinity. So are all of the numbers that I've now highlighted on my number line for the x-axis, are they bigger than or less than -2? Yeah, they're bigger than -2. So we would say that all of the numbers for the x's are bigger than -2. Great. Now we can repeat that idea for the range. Here's the bottom. It's at level 0. And here's the top, but it's also going off to that infinity. So if I look at the endpoints I have a graph that shows up on the y-axis from 0 all the way up and off the screen to that positive infinity. Are all of the y values bigger than or less than 0? Yeah, the numbers above it are bigger than, so this is y greater than 0. Quick question, see if you can answer this for yourself. Why did I not put the line underneath both of these? Yeah, hopefully you remember that because that endpoint that I'm dealing with is an open circle, right? Right here is an open circle. I'm going to use just less than or greater than, not the equal to part. So this time we actually have to make a decision on which of the 4 symbols I use instead of just 2. Last class we always used less than or less than equal, and that's because we had 2 endpoints. But this time, because our domain and our range is a little bit different and it only has 1 endpoint, we would have to choose between all 4 of the symbols. Now let's talk about how to write that domain and range in words, because that's going to be important for us. If we're writing the domain of this in words, the verbal description here would be all real numbers, that part's always the same, that are greater than, not equal to, -2. That's what this math sentence right here says. All of the numbers, all real numbers, greater than -2. This first example for the range, how you would say that out loud is all real numbers. Again, that part is always the same. And that's also greater than, that's the symbol, 0. That's how you would say this range out loud. All real numbers greater than 0. Let's see a couple more examples. I'm going to zoom in on this one so you can stay focused with me. So if we're asking for domain and range again, couple things you notice. Number 1, closed dot. Great, we noticed that. Number 2, arrow, so we have 1 endpoint. We're looking for the maximum or minimum x value. So here's my x value of -2, and the graph on the x-axis goes this way, headed all the way towards positive infinity, on and on and on to infinity. Again, my y value is at 0, and this graph goes this direction. That's where the line is with the arrow, all the way towards, since it's at the bottom, -infinity. So if I put those things together, my domain is all real numbers that are greater than or equal to -2 because of the closed dot. And my range, since I went down, is going to be all real numbers less than or equal to 0. Because we went downwards, that's where it's going to be less than 0. Those numbers are negative down there. That's less than 0. Remember, the way you say this is all real numbers greater than or equal to -2. Say that to yourself right now. All real numbers greater than or equal to -2. All real numbers less than or equal to 0. Let's try the third example. I actually want you to pause the video and give this one a shot yourself. Okay, hopefully you paused it, and if not, pause it. What we're going to do is we're going to see the domain and the range. This time, the x value is at -2, right? Bloop, -2. The arrow goes this direction. We only have 1 closed endpoint, so we're going to be writing one of the one-sided inequalities. For the domain, it's all real numbers that are less than or equal to -2, because I went the left side. Notice how this arrow, if this was like an arrow, right, it's pointing that direction. That's the left side. Oh, that's helpful. Okay, let me erase all this for a second, and then put it back. If we check out the range, here's my endpoint. It's at the value 2. And the line is all this direction on the number line, towards -infinity. So we would say out loud, all real numbers that are less than or equal to 2. This graph shows up everywhere where the y values are less than 2 on that number line. Another example here. Let's see. I do still want you to pause it and try it for yourself. Give it a shot. Okay, hopefully you paused the video and gave it a shot yourself. If we're looking at the domain, that's the x values, that's 3. And if you follow where this graph shows up on the x-axis, on that number line, it's going this direction. Is it headed towards positive or negative infinity? Negative infinity. Since this is an open circle, hopefully you noticed that, we're not going to put the lines underneath our symbols for the or equal to because it's exclusive. We would say out loud, all real numbers less than 3. Remember, you can think of the symbol like an arrow. That coloring, when I colored in that number line, is going that direction. So I'm going to use less than. The range, again, we're looking for the y value. This is as low as it goes. Even though it's a low value of 2, I'm using air quotes to say low value. That's still the lowest that this graph goes, and the rest of it goes up this direction towards positive infinity. So we would say that the range is all real numbers greater than 2. Let's write down in a verbal description again this is all real numbers less than 3 and all real numbers greater than 2. You are going to be responsible for putting these into verbal descriptions today, so make sure you can say them out loud. All real numbers less than 3, all real numbers greater than 2. Okay, now it's time for you to try all on your own. So what I'm going to do is I'm going to have you try all 4. And then I'm going to have you pause the video because I'm just going to plop all of the answers on here. And I want you to do all 4 before you check your work. Okay, pause this video because don't see the answers till you've tried it. Try all 4 and then press go again. All right, let's check our work and see how we did. So hopefully you were able to look at these number lines, the x number line and the y number line, and kind of follow where the graph is going. For this first one, the farthest left, the farthest right that this goes is 3, and we have an arrow on the other side. So 1 endpoint, 1 inequality. Now this graph on the x-axis is going this direction, so it's all real numbers less than or equal to 3. That's how we would say it. All real numbers less than or equal to 3. For the y's, the lowest that this goes on its one endpoint is -4, and everything else for the line shows up above on the number line. So it's all real numbers, and I totally wrote that wrong. Okay, all real numbers greater than or equal to -4, because it's above. See, I make mistakes too, it's fine. If you look at the second one, I'm going to the side here. We would see that the farthest to the right, my one endpoint goes, its maximum value is 1, and every other point where the line shows up is to the left. So we draw our left arrow. It's all real numbers less than or equal to 1. The y's have a top number, it's 4, and everything else is below it. So you'd say all real numbers less than or equal to 4. Switch to the third one. You have an open circle. So again, with our open circles, we shouldn't have lines underneath. The x value, the furthest to the left this one goes, is -1. That's its minimum value. And since the graph goes this direction, right, this direction is this direction, we would say all real numbers greater than -1. For the range, its lowest value is 1, and everything else is up here because it's going up, so it's going up. It's all real numbers greater than 1. Last but not least, our verbal description and our inequalities here. We have an x value at 0, and the graph, since it's going this direction, the x number line goes this direction, so my arrow should be going to the right. All real numbers greater than or equal to 0. Range, the highest value is 4, and everything else, since the arrow is going down, is down below, headed towards negative infinity. We'd have all real numbers less than or equal to 4. If you're struggling with this right now, definitely is a time to call one of your teachers over or come into tutoring, because this is pretty much the gist of one-sided inequalities for graphs with one endpoint. We're going to transition now to finding reasonable domains and ranges. This is kind of why we do domain and range. It actually makes us aware of the boundaries for different functions that we have in the real world. So let's say that we're Angela. Angela is renting a snow cone truck for a party. The truck charges a fixed cost of $75 plus an additional cost of $25 per hour. Now, hopefully we're remembering way back when that the word per right here kind of indicates that that number is being multiplied. It's being multiplied by the number of hours that we're working, okay? We go on to read, and it says the truck can be rented for a maximum of 4 hours per day. Fantastic. All right, let's write in a rule to model the situation. So our function of x, which means we're plugging in x's, we have 25 times the number of hours, so that's 25x, and we have a fixed cost or a flat fee of $75 to rent the snow cone truck. So $75 just to rent it, and then every hour that you rent it is $25. So let's say our x's, so our first coordinate is the number of hours, and we'll say that the second, the y value is the cost, a total cost it takes. So f of x stands for cost. Is this discrete or continuous, and why? So here's the thing. This gets a little complicated when you start thinking about what's going on. Do we count or do we measure hours? Now that's tricky with hours because it kind of depends on what it's representing. If you've ever rented something before, you rent it by the hour. If you turn it in 30 minutes early, they're still going to charge you for that full hour. If you keep it for an extra 10 minutes, they're still going to charge you for the full hour. That's how rent works. Kind of sucks. So since I can't charge half, I'd actually be counting this information, and it's discrete because you can't rent for a half hour. Okay, they're going to charge you the full hours. Okay, since it's discrete, that means our domain and range are just going to be lists of numbers. No big deal. So let's find our lists of numbers we can have for domain and for range. Domain is my input. My input is the number of hours. So what's the least number of hours that Angela could rent this snow cone truck for? 0. She could rent it for 0 hours, right? That's a thing. She could rent it for 1 hour. She could rent it for 2 hours. She could rent it for 3 hours. She could rent it for 4. Can she rent it for 5 hours? No, we have a domain here that says we can only rent it for a maximum of 4 hours per day. That's its domain from 0 to 4, using only the whole numbers, 0, 1, 2, 3, and 4. Its range we're going to get by inputting the x value. So I want you in Desmos or in your calculator to take this equation we wrote here, f of x, and I want you to plug in f of 0. If you plug in a 0, 25 times 0 is 0, plus 75 is 75. Okay, that's the first number in my range. Now I want you to plug in f of 1. And then we go back and we plug in f of 2. Do you kind of see what's happening here? We could charge Angela, if we owned the snow cone truck, anywhere from $75 to $175 for renting the snow cone truck. Because it's $25 per hour, so it goes up by 25 each time. That is a reasonable domain and range for this information. Let's check out Kenzie's. Kenzie pays $25 per hour for math tutoring. What a steal. That's actually typical pricing for math tutoring, plus a one-time travel fee of $15. So she's going to come to your house, $15, and then every hour that she tutors you for math is $25. The tutoring will last a maximum of 2 hours per day. Okay. So we have a couple things here. Let's highlight what's important. We have a flat fee, this travel fee of $15, and again, $25 per hour for the tutoring. Our maximum number of hours per day is 2 hours. Sweet. So Let's model this situation. So if we have f of x, that's going to be per hour, so 25x, and then plus that travel fee of $15. Our input, remember, is the number of hours, and our output is going to be the total cost again of tutoring. Is this discrete or continuous, and why? Now, this is where it gets a little confusing, because do you only tutor for 1 hour? No, because Kenzie is a person and not a company, she probably has some half-hour rates. So even if this doesn't really make sense to you, we're going to call this continuous for a good example. Why is it continuous? Because Kenzie owns her own business, so she can charge half-hour rates. And she can tutor for 15 minutes, which isn't a full hour. She can tutor for 30 minutes, which isn't an hour, or she can tutor for a full hour. So we can take halves or quarters of our x value. If we can have fractions or decimals, then it's continuous, which means we're going to have to fill out those inequalities. Okay, the domain is always x's and the range is always y's. We're going to need to give us a left number, one of those symbols, the symbol, and a right number for our least and most number of hours we can tutor, and then a bottom, a y, a symbol, and a top for my range. Okay, let's think about the situation. What's the least number of hours is my x's, that Kenzie could tutor? 0 hours. Would she tutor exactly 0 hours? No, that's not really, it doesn't really make sense. So we're going to say 0 is less than x, because we'd start tutoring, right? We wouldn't have 0 hours of tutoring. And on the right side, what's the most number of hours she can tutor? 2 hours per day. Now she can tutor exactly 2 hours per day. That's her limit, so we can go less than or equal to 2 hours. So we have to figure out what the range is. What's the output here? Well, if Kenzie tutored for 0 hours, how much money would she make? None, because she tutored for 0 hours. But $15 was the least that she'd make, because if this was 0, 25 times 0 plus 15 is 15. And again, because the domain is less than, the range is going to be less than. The most number of hours Kenzie can tutor is 15. Is 2. Wow. So if we plug a 2 in here, 25 times 2 is 50. 50 plus 15 is 65. So the most amount of money Kenzie can make each day if she tutors the full exact 2 hours is $65. This reasonable domain and range for the real-world problems are more difficult, I totally understand. And these examples used both hours, and one of them was discrete and one of them was continuous, which is confusing. But we'll be asking you questions with more obvious discrete versus continuous. Remember that to find the domain, you look at the problem. It's going to give you restrictions like this on the domain. And to find the range, you plug in the numbers from the domain. These are always your inputs, and these are your outputs.